Hello everyone, welcome to ceadar Project Season 2 and welcome to our brand new course on the power of graph convolution networks, master graph-based machine learning. So myself Roopesh Bharatwaj K R here.
So we are in the second week of the course, and today is our fourth class, the topological link prediction. So it's a blend of hands-on session and lecture, which you're gonna do.
So what we're gonna cover in this session is we'll be giving a brief introduction to what is a link prediction, what all the different types of link prediction is there, and how Neo4j can be used for like a topological link predictions. And here this week I have given a proper syntax for the topological link prediction. At the end of the session, I'll be gonna give like interactive a task for you to do it. So just a recap from our last session. So in our last session, we had discussed about creation of 20 different nodes and edges. And we have got like a couple of responses from like many people, and they have created 20 different nodes and edges, and with like a very good like connections between moreover it's like kind of like complex connections we have got it. So based on this, we're gonna build our recommendation system. So let's jump into like our today's session of link prediction. So basically, what's a link prediction? So link prediction is a task in a network analysis and a machine learning which aims to predict the likelihood of a future connections between two nodes in a network. So that's the main aim of a link prediction, to find what's the next link it's going to connecting in a future likelihoods. So let's see an example here. So this is the same example which we took from our old like past sessions, Aaron and Mary love story. So Aaron is directly connected with Christopher and Mary, and likewise Mary is directly connected with Diana, and Diana is directly connected with Jason and Paul. So here the darker the red color one are like current nodes here. So based on the link prediction, so we can see how well like Aaron is being connected with like couple of the friends of Diana. So that's the future connectivity. We can predict how like Aaron is being connected with like a Jason, Diana, and Paul. Sorry, I think I missed to write what name Paul. Sorry about it. So that's the futuristic scope of our link prediction. So in other words, so whenever we have like a snapshot of a network at a certain point in a time, the link prediction method attempts to estimate which pairs of nodes are likely to form a connections in the future. So here in our case, we can clearly tell that like J Aaron um, can form a future connections with Jason, Diana, and Paul. How in the sense like because the Mary is a point of connections between all of them. That's the a reason we say like in a certain point of time. In a certain point of time, they have like direct connections. In futuristic way of connecting them with each other, we can guess the likelihoods of the connections between two nodes in a network. So let's jump into a topological link prediction. So basically the topological link prediction, which helps us to determine the closeness of a pair of nodes using the topology or of the entire graph. Basically what it is does like in a topological link prediction, so it uses the closeness of the pairs of nodes using the entire graph history. So for example, in our old Aaron and Mary love story, we can see like how well like Aaron is connected with Diana and how well Aaron is connected with the Christopher. So now Aaron with Christopher is a direct connection. That's the current connection. So that means they have much more likelihood. And that's the main reason we have we could say like a topology of a network gives us the clear information regarding the closeness it's being connected with each other. So what are the advantages of like a topological ring prediction? The main biggest advantage of topological ring prediction is like that it does not require like additional informations. So here the topological link prediction is completely rely on the network structure, and it does not require external information or the node attributes. Basically, like in our last session, we did using like multiple node attributes like name, their age, and their location. So here in a topological link prediction, those attributes doesn't have like much more emphasis here, and it makes them applicable in a situation where attribute data is unavailable or not relevant to the prediction task. So that's the main reason why we don't require too much of information for a topological way. So another biggest reason is like computationally efficient. So in topological link prediction, like when there's like a large scale networks, which involves like straightforward calculation based on local properties of the node. So here the computationally efficient here, which is like easy to do it. And as you all aware, like how the graph is being used, it finds the connections between, and it also uses in a topological way in perspective. It looks for like the closeness of each and every node which is connected with the another nodes in a given network. So it's more or less like we can say like it can be applicable for large scale networks, and it will be much more efficient in a way. So the next important reason for like a topological link prediction is like a robust to noise and missing data. So moreover, like in a graph, we can see that there is like a lot of missing data will be there. And in a graph neural networks, irrespective of like missing values or like has a noise, it doesn't consider, and like it doesn't like takes into much. Why? Because like if there is a node is connected between another node, that's the reason when we will be computing a lot of our the prediction process and everything. If there is a missing node in that, so we won't be using like those that the not linked node basically. So that's been like completely avoided here. So here in a topological link prediction way, so this method can be robust and noisy or in incomplete data scenarios, as they focus on because of they as they focus on general patterns and relationships within the network rather than a specific attribute values. That's why we say like it's robust in noise and missing data. So next we will jump into like different types of link predictions using topological link predictions using Neo4j. Yeah, I can see as
Hey, Roopesh,
yeah,
can I ask a really
yeah,
stupid question? How,
yeah,
how do you know there's a node missing? Do you have a whole load of connections going nowhere, or is it just the
yeah.
graph is incomplete?
Uh, so that's a nice question. So how we know a node is missing? Or because like in our assignments we know like we are creating a node, but in a real case scenarios we doesn't know like if the node is connected or not. So in a broader perspective, in large scale networks like threads or Facebooks, so like one friend is mutually connected to another friend, that's called like a connection. So if they don't have like a mutually connection, that means like the node doesn't have that much relevant information or relationships to connect to another node. So in that case, we can say that's like doesn't have like too much of information, or it doesn't have like a voluminous information to do our computation here, and it has like a missing data in it. So we can say like that. Yeah.
So is it like you have an orphan node that's not connected to the main network, or do you
Yeah,
have a node
exactly.
without
Yeah.
information?
Yeah.
Okay, thanks.
So in a topological link prediction algorithms, so basically in Neo4j has like six different types of topological link prediction algorithms. So they are called like algorithmic, common neighbors, preferential attachment, resource allocation, same community, and total neighbor. So these for like 6 different types of algorithms. They are like a pre-built-in algorithms, and they are like easy to use for our like large scale deployments in a pipeline perspective, and to find the closely connected like nodes within a given network. So one important thing about this like topological link prediction is like one of the stuff is like adaramic. So as I said earlier, the aim of those topological link prediction algorithm is to find a closeness. So whatever the situation, the main aim and motto of those 6 different algorithms is to find which one is closely connected with each other. So let's get in the deep more about like what are the different types of algorithms and what is the main specific use cases. So like first one is like adaramic. So adaramic is used to compute the closeness of the nodes based on the shared neighbors. So basically, like adaramic that uses like it connects based on the shared neighbors which is allocated between a one node to another node, and based on that shared one, it computes the score. In Neo4j topological link predictions, the minimum score is 0 and maximum score is based on how well they are closely connected with each other. So as of now, like when I was trying to implement and using, I found like for my use case, the preferential attachment was giving like a very nice scores, like around like 89 to 90 scores, unlike adaramic, which was giving me like 3 or something like that. So what I want to tell you here is like we in the Neo4j, they have openly said like it's anything more than 1. It has like a very good connections here. So we don't have the upper limits of what's the like highest, or highest in the sense like how well it is closely connected. The higher the scores, it's much more like closely connected to each other. So this is the below syntax which we use for like adaramic. So this is just a single line syntax which we'll be using. So we'll be using a GDS alpha link prediction admic adar and the nodes. So node 1 and node 2. So in our example, if we use the same algorithm to kind of to find like what the score between Aaron and Christopher. Why? Because Aaron and Christopher are directly connected with each other, and it gives us like more than 1. That is like they are well close to each other. So next important thing is like a common neighbors. So basically, the common neighbors, they capture the idea that the two strangers who have a friend in a common are more likely to be introduced than those who do not have a friends in common. So basically, it gives us the idea of like the more scores for a person who is having much common in relationship. The closeness is being identified here based on the shared neighbors, which has like common and mutual relationships. So based on this information, our common neighbors works, and it gives the scores from anything above 1. So here again we use the same type of syntax here. So GDS alpha link prediction common neighbors, the connection nodes between node 1 and node 2. So likewise, we have like a preferential attachment. The preferential attachment is a measure that used to compute the closeness of a node based on the shared neighbors. So basically, you'll be having kind of doubt like, so why am I seeing like the topological way of link prediction has like a more closeness based on nodes and based on the shared neighbors, and that's very common for all the 6 algorithm does the same thing. But internally, these each and every algorithm has a specific set of like matrices which is being calculated based on those parametric matrices. So our scores does varies here. So I have given a syntax here, like the we have a person 1 is Mitchell and person 2 is Karin. So when we do like a link prediction for them, like a preferential attachment, so that's the basic syntax which we use. So we can see like it's like directly connected kind of. We can assume and we can get it. The next important one is like a resource allocation. So say as I said earlier, like resource allocations also use the same type of like a closeness attribute finding on the neighbors. And the only thing, the difference is like how well they are connected and how closely they are connected with each other. So this algorithm was released in like a much later way, in the sense like around 2014 it was released. and it was like outperforming like other different algorithms. Yeah. So I have a so this is the like a basic syntax, and it's the one line syntax which used to find the closeness of the node with the scores from anything above 1 to the upper limit. So, and one more thing is like we have the community detection. So community detection is like very important, like a way of measurement, I would say, and like how well it is closely connected. And when the communities could be computed using one complete community detection. So how well the two like different types of nodes are being connected to a same community. So and it is gives us our like the scores of like if person belongs to like same particular category of people, or like the same particular category of like demography. So it gives us much more in terms of like higher scores. Why? Because all these like nodes share their common perspectives and share their common nodes, and like near neighbors they do share. So here in a community detection, it is much more useful. So this community detection can be used for like a variety of applications, in a sense of like if we need to find like how well is the score of like a type of viruses. It will be much more easier in terms for like a biological perspectives. It is like community detection is much easier. Yeah. So and Neo4j brings us with like a single line of like syntax, which makes much more easy in a production and deployment. And next important, finally, we have like a total neighbors. The total neighbor computes the closeness of a node based on number of unique neighbors that they have. So basically, it is based on idea that more connected a node, it's more likely to receive a new links. When there is like a new connection is being gonna happen, so it senses and it gets like a new set of links. In that here, in this case, here in our total neighbors, like it calculates the score based on the like how well it's going to be connected with each other in a connected zone of more likely to happen in the future. So it calculates those predictions here. So now what we're gonna do is like I will as you know, like last week we started with a like 20 different set of nodes and 20 different sets of edges. So now I'm gonna create a like a separate breakout rooms here, and I'm gonna come into the each and every rooms, and I'm gonna basically you're gonna implement this like the topological link prediction. I'm gonna share those the syntaxes with you, and you're gonna experiment it, and I'm gonna monitor each and everyone. And please take this opportunity, and I will also be like helping each and everyone here to understand and make you to get familiar in these concepts. So let me put you in a breakout rooms, and we can have like a more personalized chats. Yeah.